Hello, everybody. Today, I want to explain about the structure and evolution of stars. Let me share my screen. Yeah. Here you see different kinds of planetary nebula during helium shell flashes, ejection of outer atmosphere regions. You see some of them are like circular or spherical, but some of them no, they have some ring somehow. And what's the cause of them? Now we can say that our sun can be something like this or this or this because it's a singular star. Singular stars become something like this with a ring. It is somehow spherical. But for stars that they are binaries, they will be something like this or this or this or this. They are binary stars. Burned out core becomes a white dwarf. In the exposed stellar core, no nuclear reactions. It becomes a dense spherical sphere about the size of the Earth and is called a white dwarf. It is so dense that electrons are degenerate. The degenerate electron pressure supports the star against further collapse. There is still thermal radiation. As the sphere cools, it becomes dimmer. One teaspoon, this teaspoon white dwarf matter weighs about 5.5 tons. Density about 10 to the power 9 kilogram over meter square. Meter to the power 3. And there is a Chandrasekhar limit, and the Chandrasekhar limit is the upper limit of the mass a white dwarf can have. The limit is 1.4 solar mass. Beyond this limit, the degenerate electron pressure can no longer hold the gravitation contraction. If the core after the giant phase when it becomes a planetary nebula is less than 1.4 solar mass or Chandrasekhar limit, then it becomes a white dwarf. But if the mass is larger than 1.4 solar mass or Chandrasekhar limit, it becomes a neutron star or supernova or a black hole. Here you see white dwarf. The more massive a white dwarf, the stronger the gravitation and the smaller the size. And we can say also the more massive a white dwarf is, the stronger is the gravitation and its size is smaller. And it has a large magnetic field. They are faint to observe and we observe them in X-ray. They are white because they are cool, and black body radiation shifted to a larger wavelength, and so they are bright in X-ray and infrared observation. Each white dwarf is the remnant of a supernova planetary nebula. And also we can say there are a lot of white dwarfs in globular clusters, but globular clusters are so far from sun, and white dwarfs are very faint. They have carbon and oxygen core. And you see here different kinds of white dwarf with 0.4 solar mass. They are so large. And then 0.8 solar mass, larger, is more gravitation. Smaller has more gravitation. And you see here 1.2 solar mass. It is too small, but it is too dense and too stronger gravitation it has. And you see the size of the Earth. Up to 20% of the visible mass in the solar neighborhood are white dwarfs. And we can say that in the past, they were all planetary nebula. And you can consider how many or how much planetary nebula we had already. Here you see the different kinds of solar mass that become a white dwarf. For example, for 3 solar mass, it becomes 1.2 solar mass white dwarf. And if the star has 1.5 solar mass, it becomes 0.8 solar mass in white dwarf. If the star has 0.8 solar mass, it becomes a white dwarf with 0.6 solar mass. Here you see the main square, and then stars go live here, and then they become a white dwarfs, and then you see the white dwarf shifted to be cooler and fainter. And you see it is so faint and it is too cool. And here the luminosity is concerned with the luminosity of sun. It is a solar luminosity, so the sun is 1, and our criteria is sun with 1 luminosity, and upper are more luminous, and down bottom are so less luminous. And here the temperature here goes increase. But here, for example, this white dwarf, it's too cool, as you see, 3000 Kelvin, and it is too faint, less than 10 to the power minus 4 solar mass. We have different types of white dwarfs, DA, V, DB, V, and DOV. And you see the different kinds of them. For example, for DA, it is nearly pure hydrogen surface, hydrogen helium shell. And for DB, it is nearly pure neutral helium surface. And they are carbon and oxygen shell, both of them, DA and DB. And for DO, it is nearly pure ionized helium surface. And for PG 1159, it exposed the core of carbon and oxygen. And here, as you see, we can say that there are different kinds of white dwarfs depending on the spectral type, DA, DB, and DO. DOV is the hottest white dwarf type, and it has nearly pure ionized helium shell. DBV has nearly neutral helium shell, and DAV is the coolest kind. It has nearly pure hydrogen shell, and it has helium shell. Also PG 1159, it is a white dwarf, is a progenitor and prototype, and it has a core of carbon and oxygen. HR diagram for massive stars, you see they follow very different paths when leaving the main sequence. The temperatures and the densities in the cores are much different reactions. And you see, for example, when the star has 10 solar mass, it becomes, it has helium and then carbon and oxygen shell core, and if it has 4 solar mass, it becomes helium and carbon shell core, and then if it has 1 solar mass, it becomes red giant branch, and then helium ignition or helium shell, helium flash. And you see different types of spectra and different kinds of mass and luminosity and temperature. For example, this one is so hot and so luminosity, high luminosity. Here you see the evolution of massive stars and less massive stars. For example, it is main sequence and different kinds of evolution of stars. And after main sequence, for example, our sun becomes a subgiant here, subgiant, and then red giant, helium flash, AGB or asymptotic giant branch stars, and planetary nebula, white dwarf, and these are for stars less than 2.5 solar mass. And for stars that has, for high mass stars, we have main sequence, and then we have giant, it is here, and then supergiants and supernova, black hole, neutron star. And these are for stars more than 2.5 solar mass. Evolution of massive stars is they leave the main sequence when the hydrogen is depleted in their core. The first few events are similar to those in lower mass stars, hydrogen, shell, core burning helium to carbon, surrounded by helium and hydrogen burning shells. Differences are stars with masses more than 2.5 solar mass have no helium flash, but it starts gradually burning. It becomes a supergiant. And for core burning, they undergo an extended sequence of thermonuclear reactions in its core and shells. These include carbon-12 fusion, neon-20 fusion, and oxygen-16 fusion, also silicon-28 fusion. And we can say what fusion will be is dependent on temperature and density. And because carbon and oxygen are not ionized, they are not visible in spectral type, and we can observe hydrogen and helium. And so white dwarfs have not any spectral type. The brightest magnitude of white dwarfs is around 11 magnitude. And iron is not fusing and I will explain it later. You see the stage for a star with 25 solar mass or massive stars. The stages are hydrogen fusion. You see the core temperature is 4 × 10⁻⁷. Core density and duration of stage is 7 × 10⁻⁶ years. And then helium flash, and then carbon fusion, neon fusion, oxygen fusion. It takes 6 months. Silicon fusion, 1 day. A core collapse, 1/4 second. Core bounce, milliseconds. Explosive supernova, it takes just 10 seconds. And the temperature will be 10⁹ Kelvin. Here you see the supergiant star. The last stage, an iron-rich core surrounded by concrete concentric shells hosting the various thermonuclear reactions. The sequence of thermonuclear reactions stops here because the formation of elements heavier than iron requires an input of energy rather than causing energy to be released. And we can say iron is not fusing when there is a iron core, there is no fusion. Elements after iron creates during supernova and shock wave of supernova. In shock wave of supernova explosion, elements heavier than iron produce. You see in supergiant star, we call it onion model. It has an orbit of Jupiter orbit and central region of a supergiant star. You see iron core, and then silicon fusion shell, oxygen fusing shell, neon fusing shell, carbon fusing shell, helium fusing shell, and hydrogen fusing shell. Evolution of supernova. Once the iron core is formed, the core contracts very rapidly and the temperature rises dramatically. Disintegration is high energy photons break the iron nuclei to helium nuclei. Electron combines with proton to form neutrons. Neutrons transport the energy. The core ends up as all neutron with nuclear density 10 to power 17 kilogram over meter square, to power 3. The degenerate neutron pressure suddenly halts the core contract. The outer core bounces back and sends a powerful wave of pressure. The pressure wave becomes a powerful shock wave as it goes outwards and expels most stellar material outward. Shock wave produces a series of nuclear reactions. The only place elements heavier than iron are produced in the universe. Supernova has 5 stages in the death of a star. The first one is just before explosion. A red supergiant star approaches the end of its life. There is no more fuel to burn and make it shine. Soon, its massive, dense core is bound to collapse under its own weight. And here you see the second is the first light flash. As you see here also, the core collapses and sends a shock wave out. For a few hours, the shock compresses and hits the envelope, thus producing a very bright flash or light from the inside of the star. The third is the flash has gone. You see, the flash here has gone. After hitting the surface at 50 million kilometers over hour, the shock blows the star apart. The core turns into a neutron star, a compact atomic nucleus with the mass of the sun, but 10 kilometers in size. In 4, you see the proper supernova. The hot glowing surface expands quickly, making the fireball brighter again. In a few days, it will be 10 power the size of the original star and will be discovered by supernova hunters. And the last one is a long time after. As you see, the remains of the former star are spread over light years of space. They keep floating quickly, souping up interstellar gas here and there, leaving a faint, beautiful glow behind. Here you see the different supernova remnants. As you see, there are different shapes. They have different shapes and different colors. We have different types of supernova. The difference of them is related to different types of supernova. They are in X-ray. We can say the first type is type 1 supernova. There is no hydrogen lines, and we can say that in no hydrogen lines left, and it has three types. Type 1 has three types. Type 1A supernova, explosion of a white dwarf in a closed binary system, mass accumulation, exceeds the critical mass and ignites the carbon fusion at the core. Type 1B supernova, core collapse of massive star with hydrogen shell lost before. And in type 1C supernova, core collapse of a massive star with both hydrogen and helium shells lost before. And in type 2 supernova, we can say it has strong hydrogen lines, which means a shock wave before supernova explosion was not as strong that removed the hydrogen shell. And it has strong hydrogen lines, core collapse of massive star with hydrogen shell largely intact. You see here the supernova spectrum, thermonuclear explosion. The two characterize a supernova. Astronomers analyze its spectrum and look for hydrogen, silicon, and helium, as well as how the star's brightness changes over time. This diagram shows how the cores of stars that produce different types of supernova compares. You see here, transition between types of star, type 2, type 2b, type 1b. As I said, no hydrogen. Here you see the classification scheme, a supernova matrix, thermonuclear explosion, and core collapse. As you see, there are different types of them. Type 1A supernova are those produced by accreting white dwarfs in closed binaries. And we can say that type 1A supernova is from binary stars and has no hydrogen and helium lines in its spectra. And supernova type 1 is the spectrum has no hydrogen or helium lines, but does have a strong absorption line of ionized silicon 2, produced by runaway carbon fusion in a white dwarf in a closed binary system. The ionized silicon is a byproduct of carbon fusion. As you see here, red giant and the white dwarf explodes. White dwarf. They are in binaries. In a type 1b supernova occur when the star has lost a substantial part of its hydrogen shell. Type 1b supernova, the spectrum has no hydrogen lines, but does have a strong absorption line of unionized helium-1. It produced by core collapse in a massive star that lost the hydrogen from its outer layers. As is a supergiant star with outer hydrogen removed, and then it goes to a core collapse explosion. As you see here, type 1A and type 1B has no hydrogen lines. And type 1C supernova occur when the star has lost a substantial part of both its hydrogen and shell and helium shell. In type 1C supernova, the spectrum has no hydrogen lines or helium lines, produced by core collapse in a massive star that lost the hydrogen and the helium from its outer layers. And you see a supergiant star with outer hydrogen helium removed, and then its core collapse and explosion. Type 2 supernova are created by the death of massive stars. They are the remnant of massive stars. Type 2 supernova, the spectrum has prominent hydrogen lines, such as hydrogen alpha, H alpha, produced by core collapse in a massive star whose outer layers were largely intact. You see here a supergiant star with outer layers largely intact, and then it goes to core collapse and explosion. You see in its spectrum, you see we have H alpha line. You see here the light curves of supernova, and you see there are different types of light curves for supernova. Also here, this from maximum and absolute magnitude are different kinds of supernova, and this is related to supernova 1987A. And type 1 supernova is a standard candle for whole universe, and we can measure distant galaxies from them. Absolute magnitude is strongly correlated with rate of decline. Faster is fainter, and apply a stretch factor to compensate for this. And you see a time from peak for it is in days, and also luminosity for solar luminosity. And you see a less luminous supernova fade fast, and luminous supernova fade slowly. And also here corrected luminosities and durations. Supernova 1978, the best observed supernova, it occurred on 23rd of February in 1987. In the Large Magellanic Cloud reached the magnitude was 2.9 magnitude. And here you see the supernova 1987A, and the supernova in here, its progenitor is blue giant instead of red giants, and it was exotic because we expected that progenitor should be red supergiant, not blue supergiant. And because it was blue supergiant, its light curve was different from others, as you see here and here. It is for blue supergiant, but those are for red supergiants. For supernova 1987A, we can say it has neutrinos were detected. More than 99% of the energy from such a supernova is emitted in the form of neutrinos from the collapsing core. Neutrino energy 10 to the power 46 joules, 100 times as much energy as the sun has emitted in its entire history. Neutrinos arrived 3 hours before the first supernova light was seen. The 3-hour delay was due to the propagation time of the shock wave from the core to the surface of the supergiant. And here you see the supernova 1987A, the outer ring, and this is inner ring, about 1.3 light year or 0.4 parsec in diameter. It's seen in 1996. Here in 2017, you see it is different. You see the inner core, inner ring in 1996 was not much bright, but here in 2017 it is so bright, inner ring. And you see the supernova 1987 during the time from 1994 until 2014. And you see the difference of them, that the inner ring becomes so bright during the time, and then it faint and bright. Here you see again the difference of them, that you see the inner core becomes so bright in 2012. You see, and then it becomes somehow faint. Thank you for your attention and see you next time. Bye.